To finish section 2.3, we're now going to start using these derivatives as we start to move into problems that require us to take the derivative. Specifically, these are going to be questions that at this stage relate to questions about the tangent line. So let's start off by finding the equation. Let's find the equation of the line tangent to the given curve, which for our first problem, let's use x squared plus the square root of x minus 8 over x minus 6. Let's use that equation, that function, at x equals 4. So we've seen this question before. We haven't done too many of them, but we've seen this. This came up in 2.1 once we established the definition of the derivative as the idea of the slope of the tangent line. We saw how we could answer this. And the way to do this, well, to find the equation of a line, I encourage people to use the point slope formula, because here you just need any xy pair and you need the slope. And I don't even care if you don't solve that for y at the end. I would be perfectly happy with that as a final answer and give you full credit. But for other people, if you only remember y equals mx plus b, well, when you get your xy pair, you have to do extra work to solve for b. So that's why I'm encouraging this formula. So 2 things. I need an xy pair. Well, some of the problems in the book, they just give you that right off the bat. I tend to only give you x. How do you get the y? You get that by plugging into the original. Remember, we're looking for an equation of this tangent line, but that point, at this point, so the xy pair on this curve will coincide with one xy point on this tangent line. So I'll use that known common point. If x is 4, I'll plug in. 4 squared is 16. Square root of 4 is 2. By the way, everybody, don't say plus or minus. If you take a square root, if you add x squared equals 4, then the answer is plus or minus 2. But just taking a square root when it's already there, it's a plus because the plus is there. If it was a minus, then it would be a minus 2. That's it. Minus 8 over 4, that's a minus 2, minus 6. So a of 4 equals 10. Some people like to make that extra note. The xy pair is 4, 10. But next, I need the slope. Specifically, the slope of the tangent line, that's the derivative. So a of 4 gave me the y, I was missing that, and a prime of 4. But before I can get a prime of 4, that's what I'm looking for, but I'm going to start off with a prime of x. So I jump back to the top. Before I jump in and take my derivative, not just going left to right, I realize I've got a couple little rewrites here. This should be rewritten as x to the 1/2 minus 8x to the negative 1. And now that I've done that, and this is what I was saying earlier, now that I've got that rewrite, I could have rewrote everything, but just having those rewrites, now I'll go here, plus this, minus this, plus that, as I take their derivatives. So the derivative here is a 2x. Derivative here, 1/2 x to the minus 1/2. Derivative here, plus 8 x to the minus 2. And the minus 6 as derivative minus 0. And this is why I talk about simplifying. So you need to plug 4 into this. And some people are perfectly fine doing that, but there's a lot of mistakes when people do things like 4 to the negative 1/2 and 4 to the negative 2. So that's why it's not a bad idea to clean this up. The 2x is good already, but the 1/2 x to the minus 1/2 can be rewritten like that. X to the minus 1/2 to the denominator is x to the positive 1/2, and that is the square root. Plus 8 over x squared, right? The x to the negative 2, putting that back to the denominator. So I didn't have to do that, but now I can plug in 4, but instead of plugging in 4 here and dealing with ugly fractional and negative exponents, it's much easier. 2 times 4 is 8. 1 over 2 square root of 4, that is 1/4, plus 8 over 4 squared, so 8 over 16. And again, the little things, do you make that a decimal? That's fine. I mean, 8 over 16, that's a half. That is 3/4. 1/4 plus 1/2 is 3/4, so I get 8 3/4. If you write that as 35 over 4, 8.75, any of those are perfectly fine with me, everybody. Any one of those. So now we've got it. That is my slope. That's my x1, y1. Don't forget to finish the problem. I know I mentioned that earlier, and I'll mention that several other times. People who know exactly what they're doing, they nail all the right notes, they get it all, and then they move on to the next problem. The problem said find the equation of the tangent line. If it just said find the slope, I would do this, and there would be my answer, I would be done. But finding the equation, I also needed this piece, and I put it all together. And again, this is not the worst. If you use your y equals mx plus b formula, there's your m, but then you'd have to use this as an xy pair and solve for b and then put it all together. But this is fine. This one actually does clean up pretty nicely. The 4's do cancel if you distribute. So you'd get 35 over 4x. You get minus 35, but plus 10, so minus 25. But again, you don't have to do that. The book always solves for y at the end, so it's not bad practice, but that was perfectly fine as a final answer. Okay, one very quick thing. I want to do another tangent line problem before we move on. And you know, any problem, anything is possible. I could have given you an easier function that didn't need any rewrites. Go back, redo the problem at the end of the 2.1 video now that you know the shortcuts. After you complete your test, you know, there's problems like that at the end of the test. You've got plenty more to get more practice with some of the basics and plenty in the homework. But I want you to realize, just because you're using the derivative, that doesn't guarantee that it's going to be a simple derivative. And that's exactly what we see right here. We're not seeing anything simple. We're actually seeing quite a bit of work. Little bit of rewrite, which led to not the easiest, but not the hardest derivative. So again, all that is fair when it comes to asking problems that force us to use the derivative. Okay, the second thing, I'll only ask about tangent lines. The book also mentions the normal line. We've already done a lot, so I'll just make a quick note here that if I've got this as my curve, and if I want the tangent line right here, that would roughly be this. But the book also addresses the normal line. The normal line, is the line that still goes through that same point, but is perpendicular to the tangent line. So just to realize, just a quick reminder, again, I'm only going to ask tangent line. The derivative gives us the slope of the tangent line, so that gets plugged in. But just a quick reminder, because there are one or two of these in the homework where they ask for a tangent and the normal line. The normal line, it's the perpendicular to the tangent line, and perpendicular lines have negative reciprocal slopes. So positive 35 over 4 for the tangent line, negative 4 over 35 would be the slope of the normal line. Okay, so that was problem number 1, finding the equation of the tangent line to this curve at this point. But I want to ask that same question, but now I want to do the function x cubed minus 5x plus 7 all over x squared minus 3 at x equals 2. This function with this x coordinates. Okay? Hopefully still not too bad, right? It's the same problem. And that's what I want you to realize. Finding the equation of the tangent line, You're using this as your guide, you need an xy pair, and you need a slope. It doesn't matter if the function is easy, if the function is complicated, if the function needs rewrites, or the function has division. The steps are still the same. It's when we get to the derivative, the technique, the shortcut we use that might vary. So I'm going to do it the same way. I want the xy pair, so I'll start. Here's the x, plug it in, find the y. So I plug it in, 2 cubed is 8, minus 10, plus 7, all over 2 squared, 4, minus 3. And I do some arithmetic, clean that up. I get minus 2 plus 7 is 5, and then 4 minus 3 is 1. So I've got an xy pair, 2, 5. Second part, I need the derivative to get the slope. Again, specifically, I need the derivative at 2. That will be my slope. But as we keep suggesting, let's get the derivative at x, and then we'll just plug 2 in. That's our better habit, especially now with the shortcuts. You know, that whole limit definition we could use using an a value of 2, that's going to be a real pain in the butt for a problem like this, but we could make it work. But especially now with the shortcuts, we definitely want to embrace. Use the shortcut, get the derivative function, okay? So right here, b prime of x, we've got our original y value, but the derivative, I'm going to use quotient rule. And this is one, again, challenge yourself. Do it off on the side, confirm that you get what I get. I'm going to do it as I write the rule. I'm going to read the rule and just fill in what I need. Quotient rule starts with derivative of the top, which is 3x squared minus 5, times the original denominator, the original bottom, minus the derivative of the bottom times the original top, all over bottom squared. And this is a situation, yeah, I could distribute lots. I can't cancel this right here, but there's so much to distribute. All I really need is this derivative at 2. So instead of doing all that distribution, I'm just going to plug in the 2. But again, careful order of operations. If you need to do a little more out, go ahead. Don't go 3 times 2 is 6, 6 squared. 2 squared is 4, times 3 is 12. 12 minus 5 gives me 7. 2 squared minus 3, 4 minus 3 gives me 1. Minus 2 times 2 gives me 4. 8 minus 10 plus 7 gives me 5. All over 4 minus 3 quantity squared. So again, I'm not just doing one tiny little piece at a time. I'm doing a bunch, but I'm still not doing too much. Certainly, even going back to just using quotient rule, if you need to write more out, this is u, this is v, get your u prime, get your v prime, then plug it in, that's fine. If you feel a little more comfortable multiplying this out, then plugging in, that works too. It's just about doing what you need. So if we were in person, I talk a little bit more about making sure you're not going too slowly with this, but at home, you do have a little more freedom with that. So let's avoid those little silly mistakes. So let's finish this. 7 minus 20 is negative 13 over 1 squared. So we get a slope of negative 13. B of 2 equals 5 gives me my xy pair. B prime of 2 gives me negative 13. There's my slope. I don't mind if you don't write these little things, everybody. We're still just kind of getting used to these problems, so I'm trying to make that note. But after you get some practice, plenty of people stop here, and then give their answer. They already know there's the xy pair, there's the slope. They don't need to write it out extra. But now I've got it. Y minus the y equals m, x minus the x. At least this time, if you use your mx plus b, at least there's no fraction in m if you have to solve for b. But I still encourage you, this will always work. Once we get to trig, you'll start to realize how ugly this can be if you start solving for b. So that's, again, why I'm encouraging you that this is definitely enough. So it's only 2 tangent line problems. We're going to do more, but we still have 2 more problems before we move on. Well, 3. The first one a reminder on finding higher order derivatives. Let's find the second derivative for each function. So number one, I'll look at c of x is x to the 10th power minus 6x to the 5th plus 4x squared minus 10x plus 7. Well, this first one is super nice and super friendly. Nothing fancy here. Yes, there's 5 pieces, but every piece is a nice simple x to a power or just the number. All the pieces are connected by addition subtraction. I can't jump to the second derivative. I'd have to start by getting the first derivative, but that is very nice and straightforward. And then I take that first derivative, take the derivative again. Notationally speaking, the derivative of the first derivative gives you the second derivative. We mentioned that. I'm just trying to fill in a little bit more of the notation, but that's what we're doing. We're not done here, and this is why, again, good habits. Don't just write equals. Always have what equals, because we've seen where we do original rewrites, so it's still c, not c prime, but this was the derivative, so that should be made clear, and I'll go right into c double prime. A nice straightforward derivative, and I'm still in a very good situation. Now there's only 4 pieces, but it's still just nice simple addition subtraction. 90x to the 8 minus 120 x cubed plus 8, and you're done. But now let's move on and take a look at number 2. Let's look at d of x is x squared minus 5 times x cubed plus 4x minus 1. We need to see product rule here, everybody. If you just jump in and go 2x times 3x squared plus 4, it's wrong. Again, that's not that you're completely lost, but you're missing a very, very major component for using the shortcuts. Yes, there's subtraction here. Yes, there's addition subtraction here, but big picture, there's multiplication here, and that cannot be ignored. So, if you at least recognize multiplication, hey, that's a product, I could use product rule. Well, let's see what happens. U would be this would be my V. Again, I'm not trying to push you too hard, I'm just trying to challenge you a little bit. If you need to write it out, go ahead. I'm going to just say and do as I go along. Product rule goes derivative of the first, so 2x times plain old second, plus derivative of the second, so that's 3x squared plus 4, times plain old first. And that's a good answer. But notice what happens when you go and do a second derivative. Going to take the second derivative, well, I still have multiplication here, and now I also have multiplication here. So this is not what I was saying earlier, that we could have like triple product rule. Triple product rule would it be if we have f times g times h. So that's not what I'm talking about here. This is 2 separate product rules. Take the derivative here, that needs product rule. Take the derivative here, that needs product rule. But if you're getting enough practice with product rule, this is not the easiest problem, but it's not that bad either. So just focusing on these 2 pieces. Just these 2. First, second. Derivative of the first, original second, plus derivative of the second times original first. That's product rule just for this. Plus, now I need a separate product rule just for this. But again, not that terrible. Derivative of the first, 6x, plain second, plus derivative of the second times plain first. So it wasn't the worst. It just involved product rule to get to the first derivative and then 2 product rules to get to the second derivative. you get enough practice with product rule, that's definitely not bad. Especially here, nothing too fancy. All the little individual pieces were still pretty nice and pretty friendly. But again, an alternative. I see product rule, and again, just thinking ahead, this is always going to happen. You use product rule, just like we pointed out, quotient rule is always going to look messy. Product rule doesn't look quite that messy, but still is always going to have those separate pieces. So for the most part, the bigger, fancier rules, if we need them, well, we need them. But if we can avoid them, it makes our work simpler, a little cleaner. So the alternative, I'm going to distribute. I'm just going to multiply once at the top, and then you'll realize I'll have a much nicer time like this one, going easily into a first derivative and then right into a second derivative. Nothing fancy at all. So I distribute. There's an x to the fifth. I get a 4x cubed minus x squared. There's a minus 5x cubed. I get a minus 20x. Again, notice I'm just trying to keep like terms lined up. That's not like, so I'm not lining them up. Plus 5. And I'm just going to do one quick line of cleanup. So x to the fifth, that is minus x cubed minus x squared minus 20x plus 5. And now watch how fast these derivatives go. No more multiplication. Just a bunch of very simple pieces, so I could jump right in. Okay, I jump right in. 5x to the fourth minus 3x squared minus 2x minus 20. And then we go to the second derivative, and almost just as fast, 20x cubed minus 6x minus 2. Very nice. Last problem that we want to discuss for now. Going back to tangent lines. We found the equation of tangent lines, and now we're going to move into another important aspect. I'm going to ask you a question. Where does the function e of x equal to 1/3 x cubed minus 6x squared minus 11x? That function. Where does that function have horizontal tangent lines? We are drastically changing the question. Before, we were saying find the equation of the line. So you were given a function, and you were either given an xy pair or at least an x value to give you guidance. Here's the function, here's the spot. Give the equation of that tangent line. But now we're being asked a where question. Where in math is answered by x. So what are the x values that this function has horizontal tangent lines? Well, what's so special about horizontal lines? It doesn't matter where they occur. Any horizontal line has a slope of 0, right? And think about this. This is actually something when we were sketching the graphs, we were drawing those horizontal tangent lines to get the x-intercepts. That's a big reason. Why do we care so much about this? But these ideas kind of link together. So, horizontal lines have a slope of 0, but they're horizontal tangent lines, so that means their derivative must equal 0. A slight retranslation here. Where does this function have horizontal tangent lines is the same thing as saying, where does the derivative equal 0? Asking that question. So how are we going to solve that? Well, we're going to need the derivative. That's the first thing. So all these questions, this was a little more straightforward. We had to take a couple of derivatives, but still literally telling us find a derivative. But now we're starting to see a couple other questions pertaining to tangent lines. It doesn't tell us to find the derivative. We have to understand that's a necessary step. So this one's not bad. 3 times 1/3 is 1. So I get x squared minus 12x minus 11. There's my derivative function. And I'm setting this equal to 0. I am solving for x. There is a huge difference between plugging 0 in for x and evaluating versus setting it equal to 0 and solving for x. If you find e prime of 0, you plug in 0 squared minus 0 minus 11. That tells us nothing in this problem. That does not help us at all. What you found is the tangent line at x equals 0 has a slope of minus 11 that is completely irrelevant in this problem. So again, I'm not plugging 0 in for x. I'm setting the whole thing equal to 0 and solving for x. Well, this one, this just needs, oops, I'm sorry. I want this to be plus 11x. Plus 11. Sorry about that. Plus 11x here, so that derivative will be plus 11. If we're going to solve this, we need to factor. This will be x minus 11 times x minus 1. So now setting each of those equal to 0, and our answers are 11 and 1. Now, how many horizontal tangent lines are there? I mean, every problem is individual. Some problems will only have one, some problems will have none, some problems can have 3 or 4 or 5. This one happened to have 2. But the big picture process, taking the derivative, being able to set that equal to 0 and solve. This, again, a first one. We'll see a lot more of this as we go on. They won't always be such easy derivatives. We'll have ones where we need product rule, quotient rule, chain rule, trig functions. But again, we're establishing the process that we're going to use.